asking ourselves, what is interesting to study in dynamics? We spoke last time we met about continuous motion, and we said that it's not really important to follow the solution of the system all the time. If you know where it is, you can say to yourself, well, okay, let me see, today at this time, where is the sun? When is my friend coming? Tomorrow again at the same time, what will happen? In other words, so we don't look at every moment of the day. You go to sleep, you wake up, you cannot follow something all the time. So what do? You study what we call discrete dynamics. So what is discrete dynamics? Well, the time here is not a continuous variable. Usually, we say the continuous variable, but here we are interested in, here, what do? We take values of time, Tn, equal to n, actually. 1, 2, 3, natural numbers. So n belongs to this set, and which means that we go forward. We don't go backward. Backward will go in an inverse function. Forward, we take the example, to which we'll be talking today, example, and it's called the logistic map. Okay. Logistic refers something to economics. How things change every day, every month, but this is just a name. That's it. Another, what I will write down for you is the following, often called the quadratic map. Because it has a parameter, this is a parameter, and it will be taken to lie in the interval from 0 to 4. You will see why. And this is the variable n at the nth generation. In fact, we will say that xn is a integer nn over capital N. So it's a fraction, xn is less than 1, as you see here, because n of n is the number of rabbits. Now, what is a rabbit in English? In Russian? Krolik. So, the number of rabbits on an island. N, capital N, is the maximum number of krolik, of rabbits that can live on the island. So there is an island here, and it has a lot of food, grass, green grass. And there's little rabbits here, jumping around here in this. But if they are too many, then they will eat the grass and they will start to die. So the population now equation is as follows. Xn, you see, is the ratio of how many there are today over what is the maximum that the island can support. So n is the generation. Rabbits multiply every year, 2 years, and their parents give rise to twice 2 children or 3 children. And this is the rate of growth, is R, multiplied by 1. So this is the linear part of the map. Because if we see xn is rxn up to here, you see that if this number is bigger than 1, 2, then the generation doubles the numbers, twice. If it is 3, more rabbits. But the more rabbits, something is going to happen. Because the island there is finite. You cannot eat the whole world, it's only an island where they live. And so, we will have to introduce a term of deaths. So this is r times xn, the linear part, and then it's minus xn squared because the rabbits die. Why? Because there is no food. When you have too many rabbits, they eat the food and some of them do not find enough to eat. So the rabbits actually, this picture, now we are going to see what happens going from generation xn to generation xn plus 1. So all we have to do now is study this simple equation. You say, what can happen? Such a simple equation. Well, how difficult can it be, right? How difficult can it be? Well, it turns out that it starts very easy, but then it starts to become more difficult. Let's, first of all, when we study finite systems, discrete dynamics, we have to see that our variable, xn, is between 1 and 0. 0 rabbits, or the full set for the island. Therefore, we are going to make sure you can draw a very nice square. This is important. Geometry here is very important, and the drawings have to be good. Good drawing. So here we go. This is 1. This is 0. This is 1. Everything will take place here. Well, let's do something red here. I'm going to now color the diagonal. It's going to be very helpful to us. So let's put out here just a dotted green line that is the diagonal on the plane. And now all I'm going to do is start to draw this function. High school, huh? We go to high school. But now we're going to see what will happen in time as time goes by. Where shall we draw it? First of all, the maximum is always at 1/2 of this function. And how does it go? Well, in the beginning, say when r, so I will draw the function here for r less than 1. Of course, bigger than 0, which is, but let's make it less than 1. Then I will draw the variable here. I'll draw also another function when r is equal to 2. And this will be exactly in the middle, right here. This is for r equal to 2. And then I will draw another one for r equal to 3. So we'll go up and down. And this will be for r equal to 3. Okay, very good. Now we draw the function. Let's now use the geometry to tell us how to follow the dynamics. We don't have to go to a computer. We don't have to calculate. We can draw the geometry. So let me suppose I give you a line, a point here, x0. What do? You want to find x1 from this function. And so, because n is equal to, so we start with an initial condition x0, we get an x1 from this equation, an x2, and so on. And then the question is, what is going to happen as we move around in this plane? And look how the graphics situation, the geometry is so helpful. I'll go to find x1 here, but I don't have to go all the way here. I can stop at the diagonal. I'm there already. Now I try to find x2. This is x1. Now I try to find x2. I go down to the map, and then to the diagonal. Down to the map, and down the diagonal. So anything I do at this value of r is going to go to 0. Suppose I start here. This is my x0, x0 prime, another road. Where will it take me? Well, it will take you to the diagonal, because you have to find x2. x2 prime. Oh, sorry, or x1 prime. x0 prime, x1 prime. And then again here and down here. So everywhere you start, you always end up at 0. Why? Because the rabbits do not multiply very much. R is less than 1. So not all the parents have children. If R is less than 1, if R is 1, it means every couple has 1 child. 2 is 2 rabbits. 3 and 3 rabbits. So the rabbits, or this is the rate the rabbits multiply. So if it is 1, they stay the same.
You can ask questions. Можно задавать вопросы, причем по-русски. Я переведу на английский, если возникает вопрос.
If you have a question, yes. It's not good if you have a question you don't understand. Don't let me talk. I can go back and say it again. Make sure you understand it, because I'm trying to make it simple. And if you draw it carefully, you will understand it. You will see why. So now we see that this is the case when R is less than 1. All the rabbits' populations go to 0. So now, what about R greater than 1? R greater than 1 starts to be somewhere here. We said this is for R equal to 2. So there is R greater than 1, it's here, between 1 and 2. And now you see, something has happened. A new point has appeared. And what are these points now that lie on this diagonal? Why is this diagonal so important? Because it tells us where are the fixed points, the equilibrium points. In other words, imagine when you are on the diagonal, you're here, then you stay there. So let's take, for example, what are the fixed points of this map? Well, we have a map, xn. This, what is the fixed points? Where all generations are equal to x for all n. So this is equilibrium. The number of the rabbits stays the same. Let's say if it is 500 is the maximum, 250, 300, and it stays there forever. Because all the xn are equal to x. This is called a fixed point, or you will find it in the literature, in the library, in the books, call it equilibrium. Everything stays the same. But if xn is equal to x, then equation 1 gives me x equals rx times 1 minus x. So there are two kinds of solutions. Let's go to the first one. I will call it what? Call it x with power with this parenthesis 1 here. It is equal to 0. If we put 0, 0, no rabbit, nothing happens, obviously. That is called, in English we call it trivial, the very simple fixed point. But there is another one that's very important. And this is when we cancel x, And we find what? 1 equals to r minus r x. Correct? So this tells me that x bar, x2, what is called, yeah, x2 is going to be equal to what? R minus 1 over r. So now we found only 2 fixed points. And you will say, what? Why is that interesting? Because suppose we are not at a fixed point. Of, let's say, the perfect case, 200 rabbits. We are at 250. What happens is this number from 250, boom, boom, will go to 200 if it is a stable fixed point. So now we want to understand if the fixed point is stable. If I am going there, to be there, will I stay there? Or will I go away? Let's take, for example, this fixed point at 0. Is it stable? Is it a stable fixed point? Yes. But when? It is stable when r is less than 1. Correct? Because when r becomes bigger than 1, this is smaller than 1. Here r is bigger than 1, here r is equal to. So for r bigger than 1, I'm making everything clear here. Yeah. So here r is greater than 1. When I start from somewhere, I will never go here. Notice. Suppose you go down close to this point. What happens? You find the function, then you find the diagonal as you iterate from an x0, then you find the function, all the orbits go away. So 0 is not at an equilibrium anymore, fixed. You know, it's a fixed point, but it's not stable anymore. The system wants to reach a number of rabbits, not 0. And what will that number be? This number. So we go up, down, up, and we arrive at this point. Here is what we call x of 2, equilibrium. It's stable. So is it corresponding to 200 rabbits? Yes, then it's stable. If the rabbits multiply more, this is double the generation. Twice, every year, twice the number of rabbits. If we make it 3, what will happen? So you now wonder, what will happen to this system, ecological system, after we raise the number of r? And you see that, here, this will happen. Suppose you start here, at this point, another x0 here, then you go over here, and then you follow the function, up, and again there. So everything seems to go to a stable fixed point. Let's take now r equal to 2, which happens to be geometrically right there. When r equal to 2, then x is 1/2. Okay, this is 1/2, and then we get, we go to 1/2 right here. This will be 1/2. So r equal to 2. Okay, so the fixed point is at the top of the mountain. Well, let's see how the orbits behave now. I start from here, x0. I go to the function, then to the diagonal, then to the function, then to the diagonal, then to the function. Whoop! Very quickly I arrived at the fixed point. This way. Well, the same thing. Suppose you start over here, wherever. Because there is a symmetry, you will go over here, and then you start again. If you start here, you go up, you go here, and you go up, you're at the same point. So now we have 2 points for r greater than 1, and even r equal to 2. x1 is unstable, the origin is unstable, and x2 is stable. And do we know the value of that point? Yes. If we put r equal to 1/2, it's located right here. 1/2. Sorry, no. R is equal to 2, I said. 2 minus 1 is 1 over 2, r 1/2. So it shows it's correct. It's there. And now, let us be more bold and say the rabbits multiply 3 times. What can happen? In nature, we see equilibrium. You put an ecological model of an island or in the jungle someplace, and you see there always are 1,000 elephants, 800, 1,200. Nature reaches an equilibrium. But it is never exactly at equilibrium. Every year, you see the elephants are 800, 900, 1,000, 900, 800. They stay there. So that means the equilibrium point is stable. This is the important thing. And now comes the question. What is the condition for stability? What are we going to ask from this function? And I should give it also a name. Call it, what do you call it? That's an f, parameter r, x. This is our fundamental equation. Okay? So now, what are we going to ask on the fixed point? Let's see geometrically what happened. Let's suppose I take r equal to 3. Now I play again the same game. I begin somewhere. Let's say I begin here, another 0 here, and I go up to here. Then I go across to the diagonal to pick my next point, x1. x1 will be found here. Then I go down to the function to find x2. And then I go to the diagonal and the function to find x3. And now starts the question. Diagonal, function. Now it seems that I am going into the point. And can you answer to me this question? What is the property? What happens here? Look at this. When can we expect to go to the fixed point? And when can we expect to go away from the fixed point? Who is the deciding property?
R.
R. But basically, as a function, this is a function, what do you see here from the function? If the function is, look at the function and see what do you need to reach the point. Why here we were able to reach the point, right? But suppose I had taken a value greater than 3, remember? For example, suppose I had gone up to r equal to 4. Suppose I just touch the ceiling and come down. Let me be careful, yeah, here. So here, I would go down, cross this line, come down here. That's r equal to 4. Now, where is my fixed point? It's here. Cross this. Is this going to be stable now? Well, look. Let's take an initial condition next to it, here. We go up here, go to the diagonal, come down, up, go to the diagonal, go to the function, the diagonal, and going away from it. So this point, so what is the deciding?
Maybe order is needed function or diagonal or diagonal function.
Yes, diagonal, no, yeah. This is the sequence from the function, yes, initial condition to the function, then the diagonal, then the function. This is all correct, this is all done. But what do you see as the property? Why does it work here? It works here, but not there. At this point, we start to go away. Why?
Maybe x0 better.
Huh?
Maybe x0.
No, why x is 0? Here, no. Here we have a very good fixed point. If r is equal to 4, let's go here. What is this for r equal to 4? 4 minus 1 divided by 4. So it's 3/4. Yeah. So this point here is located at 3/4. Exactly. Now everything is okay. But do you see the property? What happens? What about the geometrical property of the function? Well, to help you, I will do a little mathematics. We will discuss now something very common. What I tell you now, it's very common in physics, mechanics, in stability of dynamical systems. It is very important to study what we call the stability near the fixed point. Near, that's what I want. I don't know what will happen when I start here. I want to look right here. When I get close to the point, will I turn around and boom, go to the green point? Or will I go out away from the point? Who will tell me that? I will say it's obvious. The geometrical picture tells you. And how do we call the slope? Sergey?
Yeah.
How do we, the slope of a function?
Наклон, наклон,
Naklon.
наклон.
You see, naklon. Because here, let's go close to this point. Let's suppose I choose x and equals. I go to the fixed point x, and I add a small number, cn. I go close to my point here, close to the fixed point, and I move a little bit away from it, like cn. Then, what will 1 give me? Equation 1, this is 1, equation 1, we start with, gives me what? On the left-hand side, I have x plus c n plus 1. I substitute x by c of n plus x. So xn plus 1 is x plus the next iterative xn. And what about the others? Well, the other is f of r, and here I will put x plus cn. So whatever function I have. This is just an example, but this is what we have. Very nice writing. Very nice notes. Now, can you see? You can see from here. Right? Now, what do we say? Have you heard of Taylor series?
Yeah.
Ah, very good. You heard it in high school maybe, right? This is easy. Well, now comes the time to use it. We learn it in mathematics. Oh, Taylor series, Taylor expansions, convergence of Taylor series. But then where do we use it? There is a chance to use it. According to Taylor series, this will be what? F of r comma x, that's the first term in the series, plus the derivative of f with respect to x at r comma x multiplied by xc3. The derivative. And what about higher order terms? Well, we're not going to worry about, because absolute value of cn is going to be taken much, much smaller than 1. We are usually looking at very small numbers. I want to be just close to the fixed point. That means that there is another term here, let's write it, 1/2 second derivative of f with respect to x squared, evaluated at r x, times xn squared. But that term we are not going to talk about. It's higher order, and it is not necessary for us. It's much smaller. If xn is 1/100, xn squared is much, much smaller. So now, what happens here? Notice that this function cancels x, because it's equilibrium. And so we have arrived at the very famous equation that the evolution of xn plus 1 is the partial derivative of f with respect to x at a value R comma, okay, xn I would say here. The second you see, because f depends on xn. Okay, that's xn. But now xn is going to be equal to equilibrium. So, and then this multiplied by xn, and that's it. I have neglected everything else, so I have a linear function. And in front of this function there, I can write it here again because you guys over here don't see this very well. When you come here, now I have xi of n plus 1, I would say, equal to some kind of derivative of my function of at xn, r comma xn, multiplied by xn. Now comes the function. How big is the slope? Because if I choose to look at the function, at the equation, xn n plus 1 equals a, let's say, times xn. This is what this is, some kind of a. You see what will happen if a is less than 1, or an absolute value of a, less than 1. Let's say minus, plus, minus a, but it's less than 1. You see what will happen? Subsequent iterations of this will give you xn equals to what? A to the n times xi0. So I will raise a number smaller than 1 to the n power, which means xi3 will go to 0. That's when we say the fixed point is stable. If the derivative of the function at the fixed point here is less than 1, so let's go say this. This is the condition of stability. R comma xn. If this is less than 1, then we have stability. Meaning that all the orbits go back, go and tend to fall on the function. Well, that's why you see it here. All of a sudden here, that's what I was trying to tell you. What is the important thing here? It's the slope. If the slope is, now here it's difficult to say because the slope is very close to 1 in minus. Okay, minus, absolute value, we don't care. Minus, over here it is positive, the slope. Yeah, but here the slope is negative. So you see, now if the slope becomes a little more negative than 1, then you are going to have instability. So now we understood that there is going to be instability. And for example, if we go to such a case, and I will now show you also a picture. Sergey, can we turn on?
Yes. Yes. Your slides?
Yes, those slides.
Yes.
Okay, if you understood it, I will, let's not be lazy and do again some plotting.
Okay, full screen probably.
So now we find,
Full screen.
Yes, yes,
and
and
go page up, page down.
Page down, yes.
Yes, and also the
A lot of pages.
also
down.
arrows.
And so if I go here, the arrows. Yeah, this is a nice lecture about many interesting shapes. And another next time, if you like, I can tell you more about these fractals and now this kind of shape. What is the structure of this line? How big is it? And you see how the line becomes more and more complicated. This is from the fractals story. But I now would like to avoid this and go to the case of dynamics. This is Newton and a very interesting iterative scheme. Newton had a way to find zeros of a function. Huh? And so, have you done the Newton method, converging? No. And the computer, have you tried to find the zeros of a function? Solve the function f of x is 0? Not yet on the computer. No. Okay, so let's forget this. And now let's see what I was telling you about. Here we are. Here we have a function. And we have a parameter. And you see it's all explained here how the generations proceed. This is xn over there. And the depths and how fast. And now we go to plot the dynamics. Here we are. Then you see now how this all will show on the computer when you plot it. You see the exactly what we were saying before. The function. We have the number r equal to 3, which is a little peculiar. Is it going to go in? At r equal to 3, it stops here for a very long time. It seems to go very slowly towards inside. Then I take magnifying glass, look at this closer, and you see indeed it goes in because it is exactly 1. The slope at this point is -1. And that is exactly the dangerous value in between. We don't know what happens, -1. If it is bigger than -1, but positive, okay, we know it's unstable. Smaller than 1 is stable. But this is exactly at r equal to 1. So now you see that. What will happen if I want to go to higher r values? What will happen then is that this point will be unstable. And it's like you have a friend here who you can stay at his house overnight, at night. And so if it is stable, if the slope is less than 1, your friend is always ready to open the door and have a guest. You stay with me. If the slope though becomes bigger than 1, then your friend says, no, you cannot stay with me. I don't want you here. What do you do now? Where do you go? It turns out you find there are 2 friends now. How is that? Because now for r a little greater than 3. Now the rabbits multiply with a little more higher rate, not 3.2. And what happens? This old friend here, who was ready to have you as a guest, is unstable. You try to go to it, and you're going. He pushes you away. You go away, 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 and then you find 2 friends. In other words, there is at this point and this point now a period 2 solution. Something that your solution, you go 1 time to the first friend, 1 other day to the second friend. 1 to the first, 1 to the second. And the problem begins to be more interesting. Because now you say, what will happen if I continue increasing the slope? And this function goes to the top. See, that's why I cannot do all these things on the board. And I need to show the picture. Then you will see that even this friend of yours now, here, who is very, what is it? No, these 2 friends, here and here. 2 friends. You see, you go out, 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 and then you go bam, 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 always between 2 guys, 2 friends. They are very hospitable. What happens now if I go make this higher? Increase the value of r to 3.5, 3.6. Will these friends remain faithful to me? The answer is no. There will come a time when those friends will say to you, we don't want you, and then you will find 4 friends who want you. And that is called period doubling. Once you open the internet and you write period doubling dynamics, all of this will appear. It's very famous, very well known. And why is that? Because Here we are. Now here I have the function g square or f square. This is f of f. And there is a reason why. Here I can find, see, this is the second power of f, or g. I call it g here, but it's the same thing as f. This means that for the g square or f square function, these are the period 2. Now they're period 1, because they are period 2 for f. But for f square, they are period 1. So you find those periodic orbits here, and then you go and you find there is periods 4 and 8 appearing, and then all of a sudden this amazing picture comes to life. What is this? Let's see what it was. Here is our friend 3. Number 3 was here. And number 3. This is the house that was hospitable to you before you reach 3. You always go there, all the orbits will go there. If you start, in other words, here, x, this is x here, 1, somewhere here, let's say, then everything will go to that point. If you start next to 3 over here, then the orbits will go to this pum, 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 period 2. Stable, you are here. 2 friends, 1, 2, 1, 2, 1, 2, 1 night here, 1 night there. And then comes a value between 3.4, 3.5. And they also kick you out. They don't want you because it's an unstable orbit. Period 4 is unstable. Period 2, I guess, is stable. And then you, in between here, you have 4 friends. You start from here, you go to this branch, down. You go back to this branch, you come back to another branch. How do I get rid of this? Okay, we got it. So, here you went down, bam, bam, bam. You reach this point, this is unstable now, and now you go. You don't go like this, careful, 1, 2, and then 1, 2, no. Because the dynamics is always the same game. It's like playing tennis. Here you have 2 friends, play tennis, throw the ball, your friend throws it back. This is double tennis. Yes, this guy hits the ball, and the other guy over there hits the ball here, then he comes back, and then your other friend here must pass the ball. So this happens to be, and now you see the motion is more complex. All of us, and this is all for rabbits, and for a simple model. That's how nonlinear dynamics can become very, very complicated. But nature is complicated. And this is such a simple equation. Mathematics has very, very good property of producing models. It's a model, a nonlinear model. And all of a sudden you see something that now, by now, we have verified this in experiments. Not with rabbits and with all of that, but with experiments with water, heating water, and the temperatures go up and down, and then they see that they do this as period 2. 1, 2, 1, 2. Then they heat the water more, and it goes 1, 2, 3, 4. And it repeats, but there is a period 4. And after period 4, there is period 8. 1, 2, 3, 4, 5, 6, 7, 8. 8 friends. And you see, this is how we reach chaos. That's why these systems are very interesting. And now, because I would like to, so you see, this is more serious. Mathematicians have proved that there is all this road to chaos. This is called a road to chaos. And you reach r equal to 4, and nothing is stable in 4. Here there still are some stable. There's a stable period 3. 1, 2, 3. And there is also similar phenomena occur. I explained here. Okay, let's leave this. Oh, come on. And so, but here it is very chaotic. The motion will be very chaotic. So now that we saw this, and that many people have studied it, we've seen it in experiments, let's say to ourselves, how about a simpler model? This is too difficult. G is G, and it's a parabola, and then it's a parabola of a parabola. It's very difficult. Can I solve a simple? And now we come to games, children games, logic. And let me tell you what is the simpler game we can play. Okay, so far, I want you to remember that this is the way we find stable fixed points, right? F of x equals that. This is the condition for stability. Remember these things are going to be useful to us. And now we forget about rabbits. By the way, you see, rabbits here will be very happy even here. If they multiply 3.5 times every generation, then their numbers will just change by 4. You have what I was saying before. 350, 550, 400, 500, 350, 450, 400. So the numbers will just oscillate and everybody will be happy. But as you go further, now it's becoming very chaotic. And then nature loses equilibrium anymore. And the rabbits will be very happy. And so they keep the numbers down to 3.5 rows. So we are getting some conclusions about real life. This is how life can be modeled. This is a biological population model, the logistic equation. And now, a smart student says, Mr. Bountis, I thought of the following model, simpler equation. I give you a square, you like squares, very good. So I'll give you the square from 0 to 1, 0 to 1. I will give you your diagonal. You seem to like diagonals, so I will plot it for you. So student. Very good. And now, I will give you a simpler function than this, than 1. My choice would be a triangle. I am not what people call they call it the triangle map. Some people call it also the tent map. You know the tent? Indians, American Indians have the tent, and they live inside a tent. So let us consider the tent map, which has the following beautiful picture. It is, let me write it down. Yeah, it is xn plus 1. Now it's piecewise continuous, so I will define it as follows. It's r times xn for xn greater or equal to 0, less than or equal to a half, up to the middle. And it is r1 minus xn for xn greater than the middle and less than 1. But if you plot this, this is what you will get. Any blue color? No. Let's see. Suppose I take, now you tell me, what about R? What is R? Now R, the top, R is equal to 2. So R is going to be R greater or equal to 0, less than or equal to 2. Why? Because the top function, up here at 1/2, this is the top. This corresponds to R equal to 2. And from here, we go down to here. A beautiful triangle. I like to draw. I'm used to now. Nice isosceles, isosceles triangle. Equal sides. Now, fine. What other, what is R here? R equal to 2. Because at this point, at xn equal to 1/2, multiply R by 1/2, and you get, when R is equal to 2, you get 1. So this 1/2 goes to here. So that's R equal to 2. What about this plot here? There is a very in-between plot. This is r equal to 1. R equal to 1. On the diagonal. So this is very special here, because if r is exactly equal to 1, then when you go here, you stay here. Every point here is like a fixed point. If it's all on the diagonal, then it's a very exceptional case. Just only for r equal to 1. What happens, however, when we take a value r less than 1? Here. How about this? What will happen under this map? And now, our very smart student who likes to study such enigmas, problems, puzzles, it's like a puzzle. He says to me, okay, Mr. Bountis, if I understand you well, then I think that for all these triangles, 0 is going to be stable. Just like your previous, we erased it. The previous picture. You started from here, you go to your function, then you go to the diagonal, then your function, diagonal function, and this point is stable. You start from here, same thing. You go to your diagonal, down to the function, diagonal function. So it's like before. 0 is stable. Good. Now you say, suppose I come to r equal to 1. Now, above r equal to 1, there is also r equal to 1.5. Before we reach 2. There's another intermediate case. Let's plot it with green. Let's say this one here. Yep. What am I doing? I should stop somewhere. It's here and here. Right? So this case is, let's say r equals to 1/2. Something like that. 1. On the way to 2. Okay? And now, let me draw it a little higher. Okay, here, and there. You follow me? Now, I ask you the question we saw before with the previous function. This point is at the intersection of the function and the diagonal. It's here. So it is
Fixed point.
fixed point. This is fixed point. Every intersection of the diagonal. Question. Is this, what is your first name?
Misha.
Misha. Okay. What is going on, Misha? Can you tell us what will happen near this point? Is this going to be stable? And if not, why not? Think about it. That's why it helps if you have your like your name?
Артем.
Huh?
Артем.
Artyom. And Artyom is plotting very carefully. Yes, you have to do it carefully to draw. Right? So Artyom, what do you think will happen now? If I start from a point here, I go to the function.
I think it's a stable point.
Huh?
I think it's stable point.
You think it's stable? Let me see. Let me see. I go here, Misha, and then I go to the function. Okay? Well then, if I was exactly at the fixed point, yes, I go to the fixed point. But let's suppose I am a little bit away. So I go to this point. Right here. I go to the diagonal, right? I fall down to the function. Then I go to the diagonal. I'm sorry, Misha. Just do it. What is the reason? I cannot go back to that point. I'm going away. Let's take this one for example. Look, what is the reason? What's happening here? Remember, R is the slope. R is the slope. If R is bigger than 1, and what is the slope here? Here the slope is exactly R equal to 1. Here, there it is. Next to it, it is higher than 1. So the slope of this function is negative, of course. Bigger than 1, you see. So they are all unstable. There is not a single guy to take you to his house. Very unhospitable town. You never go to that place. There's nobody who will take you in. There were, if there was not one, there were two, there were four, there was always some stable periodic orbit. Here, all the periodic orbits are unstable. So now what happens? You start to move, and there is nobody. And yet all the motion is inside a square. What happens now? There will be an orbit, a solution, which will go around and around and around and never stop somewhere. And all of this with very simple dynamic function. The simplest example, the 10th map. And so you see that when you, let's suppose you want to study a periodic orbit of period m. What does it mean to have a periodic orbit of period m? It means we have a point x1. This point goes to another point x2. This goes on finally to a point xm. Right? You generate the sequence. And then xm, what? Goes back to 1. As xm continues to x1. And then the same thing. This is called a periodic orbit. X1 leads to x2, leads to xm. And now, one may say, okay, these are periodic orbits. Okay, that will be period 2. x1 leads to x2, to x3, to x4, and then back again. So, what do you see about periodic orbits? What about their stability? Well, you see, this happens after f or g or f, okay, f, to the m. So every point of this period, xi, goes back to itself, I2, after m iterations of the map. You take xi, you multiply, you compose the function m times, and you find xi. So what happens? Periodic orbits, conclusion. Periodic orbits are fixed points of an m, let's say that, yeah, m periodic orbits. Periodic orbits with period m are fixed points of an m m iterate of the map. So what do I do now? I build the function g of xn, comma, nu maybe, comma r, and I take it to the power m. And every single point, I think I said it already here or something. Yeah, I said it here. Every point of the periodic orbit, like, okay, I rewrite it, xi hat, goes to itself, xi hat. And as I wrote it here, also for g and the other line, so we have it. So it is our fixed points of an m, which means that if I know these points are fixed points, but of a complicated map, but fixed points. What is the stability of a fixed point? Stability, this is now a map, U of M, a big map, F, some will call it F, on to this point, come back to this point. So the stability means that the derivative of this map with respect to xi, right, must be less than 1. So as we did before for the fixed point, you see how convenient the analysis is here. This is the important conclusion for stability. It still is the same thing we knew before, but this didn't have a power. This was for one point, equilibrium point. Here we have a periodic orbit. So you have to go m times around, return to this point, then take the derivative and find if it's less than 1. Well, but in calculus, there is what is called composite differentiation. We take a function of a function, and how do you differentiate a function that is the function of a function and all of this, right? This is composite differentiation. First, get the first derivative, right? Then add with the second and the third, and so on. And when you do that, this is the composite derivative. Then you find that here, the derivative of a function m prime of x sub n, some point of the orbit, xk, let's say, the derivative of the absolute value is equal to the absolute value of the derivative of the single function at x1, comma, mu I say, or r is better. Yeah, okay, let's call it r here. Stick to this. Times f prime of at x2 point, I don't want to write r all the time, dot, 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 f prime x hat m. So you have to check all the derivatives, but a single function derivatives at x1, at x2, at x3, and all of this for stability has to be less than 1. So this is not so difficult after all. Yet because this complicated derivative, f to the power m prime derivative, is now what we know from calculus, the product of the derivatives. And in fact here come all the points of the periodic orbit. So when you see this, you say, do I have a chance in this map to find stability? All my slopes above are equal to 1. Are not up to the red. The red is easy. Below the red, everything is stable. Above the red, when r is bigger than 1, I have such points. But all of them have a derivative greater than 1. So this is bigger than 1, this is bigger than 1, this is bigger than 1, so they're all unstable. So not only this guy, the fixed point, all the periodic orbits are unstable. None of them will stay there. So where will the orbit go? Will wander around everywhere. And in order to finish slowly about this, because next time we can say more about this problem. It's very interesting. And I'll tell you why it's interesting, and then we will stop there and study this next time in connection with fractals. But for the time being, I want you to, as a game, play with this exercise. Try to build this map and simply define this and try to play with it, try to find periodic orbits. And because you want to find periodic orbits, let's do it ourselves. Let's find the periodic orbit of period 3 now. Or period 2 to start with. Where is period 2? So this will be a nice game now to play. I told you they will all be unstable. Unfortunately, this formula here tells us that all of the periodic orbits will be unstable. But how many are there? Is there one, are there two, three, four? How many periodic orbits are possible? And now, to find out, let us draw the picture again. Don't be lazy. Draw again a square. We have a square. Back again to the square. We have, of course, our beloved diagonal. Yes. Right. We have our function bigger than 1. We said below 1, everything beautiful. It falls in the whole of the 0. We are interested above r equal to 1. So our function should be somewhere here. Let's see. Up here, I don't know, up, down here. Good. So here we are. Now, what is period 1? This point, fixed point. We said that. Now I ask you to find period 2. As I was promising to you, I promised you that you should find x1, go to x2, and then back to x1. That's a period 2. x1, x2, x3, then back to x1. Period 3. These are called cycles. Cycles. And they're very, very important. Periodic orbits. Well, okay. Then what should I do to find period 2? How should we start? Red. Pick up the red. Now, suppose I start, remember, after one time I have to come back. Suppose I start, don't do everything, don't wait, don't write anything. Suppose I start from here, say here. Then I must go to the other side, because if I stay too far here and I go 1, 2, then it's finished. So I cannot have period 2 on this side. I must find out how to go to the other side. So let's also plot the vertical. From here, 1/2. Good. So to get period 2, I must start from somewhere, go to the right, come down, and return there. Ah, I think I found it. Some must be somewhere here. Let's see. Go up. We go to the function. Closer perhaps. Closer here. Let's see. I start from here. I go to the function. Wait. Then I go to the diagonal. Then back here. Whoop! I got it. There we go. I found it. Notice that if you go to the right, then you miss this. You stay always on the right, always on the left. You have to be at a point that goes this. A unique period 2. What are the, it consists of 2 numbers. The number is x1 hat. And right here there is x2 hat. Can we find those from the equations? What do the equations tell you? You are here at x1, right? Here, and you wanted to find x2. So x2 is equal to r times x1, because we are on the left side of the dynamics. So here we multiply by r. But now that you reach x2, you want to come back to 1, then x1, to come back to it, must be what? What should I write now?
R multiply 1 minus
1 minus x2, very good. Because I am on the right, so I multiply, and now these are the equations. This is high school. All of these things are simple mathematics, but they are very deep, very important. And it has a lot of theory behind it, of course, because now we realize that we can make a function, and that if we call this side of the box left, and this side of the box right, then the period 2 I find has a symbolic representation in symbols. It is RL infinitely many times. RL. Now we start to introduce symbols. I don't care where it is. What is it doing? Is it playing to the right and then going to the left, then back to the right and to the left? Okay, and that's a period 2. Now, can you help me find period 3? Okay, with me. I will not do it, but with your help. Let's go back to draw the same picture again. I tell you, don't be lazy. So, just to have to convince ourselves that what I'm saying is right, that there is, it looks like a very simple problem, and yet it has a lot of complications in it. Let me try again, because I don't want to mess up this. Again, I draw my square. See, you have to be careful with your square not to miss that. Now, and I will ask you, we'll put the diagonal, always. And we take a function as before. Goes from here up to the middle somewhere, and then down here. Good? All right. 0, 1. And let's put also the main perpendicular symmetrical axis. Splits the triangle in 2 equal sides. Now, who wants to try? How do you make a period 3? Think about it. In your, hey, I see very nice figures. You guys are good at drawings. You see? Mathematics is also geometry. Not only algebra. How can we build a period 3? I would say, for example, that in a symbolic representation, I have to stay 2 times on one side and then to the left. Then maybe another 2 times to the right and then the left. Okay? Maybe that's interesting. So I should be looking for something that stays either to the right, or I will stay, or there is another one, L, L, R. Twice on the left and 1 time on the right. Maybe we can look for this one first. Twice on the left, huh? What do you think? Any ideas? You see, I started here, I found my period 2. Now I say it is possible to stay 2 times to the left. So I can start below, go twice here, but then I have to go over here, boom, and come back. Can you do that? You see the idea? It's a unique periodical. It's not, you cannot change it, move it around. It is unique. It has a unique solution. What will that solution be? With our equivalent formulas, we can find it. Period 3, we're talking about period 3. In other words, yeah, period 3 with index 1. There is 1 period, more than period. Period 3. What is this period 3? It starts from the left, stays on the left, and goes to the right. Huh? So it must have such a representation. x2 is rx1. We're on the left. x3 is also on the left, so it's obtained from rx3. But now we're on the right, and we want to come back. So then we come back to x1. We have to multiply r by 1 minus x3. You solve the system, you have your period 3 solution that does this. In a similar way, you will find one that stays 2 times to the right, which is a little bit more difficult to see technically. I don't know if you can see it, how to do it, yeah. But you must, if you want to go to the right, you must go once to the left, huh? Once to the left. Go to the right. Now, if you go down and here, you must stay on the right. to have 2 points. Well, there I have RRL, RRL. So you must find one that goes to this point, comes down, stays here, and then goes back to the other one. And that's the other period 3. That's this period 3. This one I found for you. This is it. You can solve it, you can find all these coordinates. And if I try to do it by hand, I will have to start from here, let's say. Go this way, but if I'm not careful and I go to this point, now look at it, go here. I go up and down and this, I should reach this point. So I must choose a point that will be in my second direction close to this diagonal. So maybe I should choose this point first. I go up, and I now must go all the way up here. And when I go all the way up here, I must go here, and then I have to fall down to here. Now, I'm not a very good drawer. I didn't do a very good job, but you see the idea. It's possible to have, if you are doing carefully, you see, I go here, 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 up to here, and then I come here. The other one would be, as we said, and you can find it also, if we start from here, we go here, we go here, down, down, here, and then back to the function. See how I stay here. I go to the right. I go to the function, but I have to stay here, right? So that always gives me trouble. Here, maybe I start from here. I go to the right, I find one here. I go to the left. Now I have my second point. Then I go here, here, down, bum. Yeah, I guess that's something. Yeah. So the red dust is the LLR, and the other one is RRL. I stay twice on the right and go to the left. It's a nice game. In fact, you can prove that there are all kinds of periodic orbits. If you go to period 4, RRRL, RRRL, or LLLR, LLLR, and you start to see the geometry, all of it. And all of these guys are unstable. So now we see that this is a kind of chaos that we find in real life. Now, in life, things are not absolutely chaotic. The weather, even the weather, comes back to being hot and then cold again and hot. And it's not so chaotic. Even the stock market, sometimes prices of commodities go up and down, prices go up and down. It looks chaotic at times. And so many things are how to say, unpredictable. But this one here is completely chaotic. Everything in real life will have a little bit of order, just like the other one we saw with the rabbits. There were some period 4 that were stable. Period 8 was stable. There was a kind of stability, and that's why that is a more realistic model. This is a game, a toy model. And finally, I want to finish today with giving you problem to think about before next time, and to see it. And I will just start it. And I will not tell you what happens in here. Just start it. Let's suppose you say now, why don't we take R bigger than 2? Just to see what happens. So let's, again, draw our famous square. Now make a big one. I'll try to make a big one because this is really more complicated. Okay, we did it. We have a function that goes up Shall we make the function by red or not? No. Let's make it black. So let's take r greater than 2. I don't know what will be greater than 2, but in fact, it will be like this. Let's take the middle line here. Draw the function, it will take us here, and then it comes down here, and goes here. So now the house has a hole above, and the smoke from the kitchen, when Mama cooks, smoke goes up from the hole outside. Now, to understand this, we have to be, a little careful to be very symmetric here. In other words, it should go by this point here, symmetrically, come down, up. Have to be better with my drawing. Okay, and now we have a picture. All right, now, who is going to go out? Let's find out. Don't forget our favorite good friend, the diagonal, right? Always the diagonal. Dividing the picture. Okay. Now, I continue now to draw. I take this point here, project it down to this. And take this other point and also project it down. So this is, how do we say that in Russian? Chimney. The house has every house, where the smoke goes out of the chimney.
Труба.
Truba? That's a chimney,
I don't know the word. How do you spell it?
Chimney is when you have a house. Truba, is it? You have a house.
Can you write down the word?
Chimney, yes. Chimney. Chimney, okay. You have a house here, the door, windows, everything. And Mama cooks food. And there is here the chimney.
Труба, да, дымоход.
Demakhod.
Дымоход.
So how do we write it?
Дымоход.
Demo. A.
Second letter E.
Second letter is E. Oh yes, okay. Right. Demo. Hod. Hod.
Yeah.
Okay. So it's a demakhod. And things go out. Well, that's what this is. Because now you say, how do they go out there? Well, let's see. This kind of double hole here, where it goes down the house, is a very interesting part here. This means, and now that I have this guy, I can now draw these lines here all the way. See, this is a little bit of work here. And I find a horizontal channel, the horizontal region. Now, okay, we got that. Now go here, take this point, and project them down to the horizontal. I told you you have to work a little bit. Go down to the horizontal. You go to the right, here, and project this down to the horizontal. And this. Okay, I didn't do anything wrong. I just drew my lines on the picture. And now I want you to see what will happen to these guys. Here, let's take for all these x's here. This is 1, right? This is 0. And this is 1/2 here. Now, from this point to this point, all of these, boom, boom, they go out with one iteration. Right? They go away out of the demo hall. They go out, they go here, go to the diagonal, but the diagonal is outside. Diagonal goes down and finds the function somewhere here. This continues down here, this line in here. So boom, 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 you go out to infinity. Fine. So there you go. All of these guys are gone after one iteration. Go away. Now let's look at these guys. And I will call them here. This I will call I1. And this region I will call I2. Now, what can you tell me about this point? They go out?
А,
Huh?
I don't know.
Say it in Russian. Say it in Russian.
Если мы начнем из них идти, то тоже улетим через дымоход. Ну, отразившись от диагонали, мы
Right.
тоже улетим.
Yes. So with two iterations, where is the map? This is the map. With two iterations, they jump out
Yeah.
of the house. Right. So indeed, this point goes here. Every point now is in this line and goes out. This point symmetrically. They go here, so the first iteration is in. The second, however, go here and boom out. So now we have lost two more points. But now, how can we continue this? Can I erase? I erase this. Gone. Away after two iterations. And this gone away. How do we continue now? Well, here is the secret I tell you, is to simply continue drawing these corridors. When I'm careful and my geometry is okay, I draw this up there. You'll see what. What about this one? Let's go up there with this one. It has another couple here. Yes? And now we find some other things here. Now there is another such line here. And so I can draw horizontals up to here and here. And go all the way to this point, little point. Oops. And now I found, if you go here one, then you go here, then you go to the diagonal, then you go up here, then you go here, and you go out. So this and another one here. Oh, there it is. Here it is. There it is. There's my other region on the left. This one also will go once, two, the diagonal, up, and still inside. Up here, boom, lost. So now I have lost these guys and these guys. How many? One, two. What about here? This also. Some will go here and here. We'll see what. But now I have lost this and this. And here also I should be careful. We should be able to do that here also. There's another. You see that Y?
Another corridor on the top.
There's another corridor on the top.
Only two intersect diagonal.
Very good. What you mean this one here, huh?
Yes.
Yes. Here it is. So we found another one here. Okay. And that one, it should be. No, here. I was looking. Here, this is it, right. Yeah, and there's the other one. We are interested in the dark sides of the triangle. So now, as I did before, I'll take this point down, right, and this one down. Okay, same as I did here. Erase it. I'll take this one down and this one down. Erase it. And now I have 1, 2, 3, 4, 1, 2, 3, 4.
7.
8. We had 2 in the beginning, solid ones, and the one in the middle flew away. Then we had 1, 2, 3, 4, and the middle go away. And now I have 1, 2, 3, 4, 5, 6, 7, 8, and those go away. Question, what will happen in the end? How many will stay? Do you think that
So, power of 2. Степень двойки.
power of 2, they leave? So what will happen in the next iteration? Every one of these black guys will have a corridor in the middle that will leave after 4 or 5 iterations. So cut 1, 2, all of them in the middle, right? And this, and that will be 16. So more and more holes. How many do you think will stay? All of these go away. So will anything stay? It seems not, huh? It seems not. Indeed, if you put it on the computer, try this. Take this map, r equal to what? A little greater than 2. Don't make it too big. R equal to 2.5. Take r 2.5, so you have a hole here. Now put on your line here 1,000,000 points on your computer. 1,000,000 points. Maybe 10 million. And later on, you will see that for a long time there will be some black points here remaining. Many of them are leaving, but there still are black points there, still remaining after 1,000,000 iterations. You wait a little longer, and you don't see anything anymore. So you say, I was right. There is nothing. And then you start to think, wait a minute, this stupid computer. Computers are not always right. What has happened? How about period 1? It's always there. When you are here and you go up to this point, you stay there. It's unstable. If you move a little bit, you go away. What about period 2? All these things we found, are they, were we dreaming? All of these things are here, and these don't go. So what happened? The computer cannot see them. Why can it not see them? Computer doesn't see them because they are too small. No, not too small. They're points. You could put them exactly, but they are unstable. Any small error, the computers make very small errors. Computer cannot see an unstable periodical. Cannot, because it doesn't know exactly how it goes. It loses it. Neither can the computer, no, they cannot. And yet we know, as human beings, we know there are infinitely many periodic orbits. We are generally here. They don't fly away, but they are unstable. So any small movement, will go away. So you see, don't believe the computer. You believe your mind, you think, and you say, numbers. Now we have rational numbers and irrational. Rational numbers, yes, the periodic orbit here will be given by some precise values. Yeah, and there is countable, right? Periodic orbits are countable. Period 1, period 2, a few period 3, more period 4. I can count 1, 2, 3, 4, 5, countable. So is that always there? Only countable ones stay? You see, I will not tell you more, but you realize that what do you know about simple mathematics of an interval? It has holes. What are the rationals? Where are the irrationals? Did we understand that? And this simple example shows us that we have to be careful, very careful, what we say when we do mathematical operations, because our mind is better than the computer, and we can judge. Okay, I kept you enough, but it is an introduction, right? It's a nice way to learn about chaotic systems and other stuff, but nothing beats an example that you can do at home, and you can study it and think about it and draw it with your hands, put it on the computer to find out if I'm right. Say, Bountis is right, let's try it. And you will see that the points will stay there for a long time, because we go many points. Eventually, there will be nothing done left, and the computer is absolutely wrong. Not only everything is here. I will explain to you another time why there is more than what you think here. Okay, but at least we understood periodic orbits should not be kicked out of the window. They are there. Here they stay. Okay, thank you for your attention.
Thank you.
Спасибо большое.